Gwen.
Yes, Doc.
Sa concept map akong nakitaan sa share file ni Jessica. The usual problem that I have is when I try to expand and it was expanded, but I still cannot read the fine print. Kaya kuridas magutanan. So it's difficult to know, to check on it.
Can I ask for each group for Dr. Meneses topic on
Protein.
Amino acids, Doc. Protein.
Amino acid, protein.
So amino acid and protein. Can you make it bigger? And then if you can have multiple, not just one, it's okay, so that Dr. Meneses will not have difficulty grading your concept maps. Just resubmit it, please, to your respective facilitator.
Email it to me na lang.
Email to Dr. Meneses. So corazonmeneses@cim.edu.ph.
corazonmeneses@cim.edu.ph. They know na because they have submitted their output naman sa synthesis in the orientation week.
So you can expand it. I think you can screenshot it and submit to Dr. Meneses, so she don't have difficulty enlarging and viewing and grading. Thank you.
So, can I start na? After me, Dr. Success will follow, right?
Yes, Doc.
Okay. Because of time constraint, okay. I would prefer actually the way it was being done by Dr. Pipito, meaning to say, if I put up a PowerPoint that you can see, somebody will just comment on what they are actually seeing. Meaning to say, I will not call anybody. Everything is volunteer. I will count silently by myself, 1, 2, and 3. If there is no response from the class, I will talk about it. Okay, so for the chemistry, I prefer that you participate. And then when we go to metabolism, then I will just be the one to talk about it. Is that okay? You may or may not mention your name. The reason for this is if you say it, you actually will remember it better. That's one. Second is, I am assured that you are there listening to what I am trying to transfer the knowledge on the chemistry and metabolism of nucleotide is all about. Okay? So again, good morning, everyone. So, okay. So in the chemistry, these are the topics that we will be talking about. Okay, so this is the first slide. So can anyone say something? Look at the structure presented to you. Okay, so the first slide is showing to you that the term nucleoside referred to the heterocyclic nitrogenous base and the pentose sugar in the form of ribose or deoxyribose. And the tide, nucleotide, is made up of the nucleoside plus 1, 2, or 3 phosphate group at 5' carbon. Okay, that's why it is deoxyadenosine 5' triphosphate or DAPP. Okay, is that clear? So in essence, a nucleotide is made up of three components. The nitrogenous ring structure, which is the base, then the pentose sugar, which is ribose or deoxyribose, and the phosphate, which either be 1, 2, or 3. Okay. Now, still silent. Okay, I will just go on and tell you what you need to remember. I said from the very beginning, when I was introducing metabolism, okay, first you have to appreciate how the structure looked like so that you can follow how it will be formed. That's one. So this is very important for you to have an idea and appreciate the anabolic pathway of any molecule that will be formed in the body. Okay. There are actually two bases. One is 9-membered ring form, which is actually a double ring. Take particular note of the numbering. So it is counterclockwise starting from N1, the first N that you encounter in the 6-membered ring. So you count first the bigger ring and then you continue to count in the smaller ring. Take note that you have 1, 3, and 7 nitrogen atom where it is positioned. Okay, 1, 3, and 7 is nitrogen. The rest are carbon atom. And of course, it is a double band or conjugated ring form. Now, there are two kinds. This 9-ring structure is referred to as your purine base. We have adenine and guanine. In adenine, at carbon 6, you have an amino group. In guanine, you have carbon 2, an amino, and at carbon 6, an oxo group. So 6 amino purine is adenine. 2 amino 6 oxopurine is guanine. If you add a pentose sugar, it becomes adenosine, guanosine. If you add one phosphate group, you have adenosine monophosphate or adenylic acid, guanosine monophosphate or guanylic acid, or AMP, GMP. You add another phosphate, it becomes ADP, another phosphate, it becomes ATP. Okay? The X there that is seen in the structure of guanine on the left side, that is N9, that is where your ribose or deoxyribose will be attached. Next, the other 6-membered nitrogenous ring is your pyrimidine. There are 3 of them: cytosine, uracil, thymine. So take note where the substituent group is attached, okay? Then that is how you will call them. With the sugar added as a nucleoside, we have cytidine, uridine, thymidine. And then when you have the phosphate group, so cytidylic acid or CMP, uridylic acid or UMP, thymidyllic acid or TMP. Take note of the numbering. It is clockwise with the N1, okay, as the number 1, the one below. So the numbering is different, okay? This is important to know the different atoms of the ring when we go into the de novo biosynthetic pathway. Okay. So if it is purine, the attachment is between N9 of the smaller ring to the ribose sugar, to carb C1 prime. when there is a prime attached to the carbon, it means to say that is the carbon atom of the pentose sugar. Now, there are two configurations, which is anti or syn configuration. The one on your left is the syn, the one on your right is the anti. Oh, take note, the predominant conformation is your anti, but in the summary of the chapter, it becomes syn, so that there is an error there. So it should be anti. So N-glycosidic bond is in anti-conformation. So it is between the anomeric, which is the C'1 of ribose, and the N9 of urine, or the N1 of pyrimidine. Okay. Then these are the terminology of the bonds. Usually the phosphate group is attached to carbon 5. Okay. Then that is the alpha phosphate. It is a phosphoester bond. We will be emphasizing on the connection of the next, the second, and the third phosphate group, which is the beta and the gamma. The bond here is known as your phosphoanhydride bonds, or just anhydride bonds. These are very important bonds because it has a high transfer potential. And it can precisely the reason why ATP is needed in condensation. It is capable of linking or forming the bond to connect the monomeric units of the macromolecules. So the first is phosphoester, the last two is phosphoanhydride bonds. The name of the first phosphate is alpha, beta, gamma. So be familiar with your Latin alphabet. Okay. Now, in addition to that, those are the major bases of purine and pyrimidine. We also have the modified or the unusual or the minor bases, which is seen in your nucleic acid molecules. So the first one is pseudouridine. It is pseudouridine because the linkage between the pyrimidine uracil, okay, to the sugar is between C'1 and C5 of the ring. And this is found particularly in the tRNA. Then the second one is also very important. This is methylation by S-adenosyl methionine of a UMP of preformed tRNA to form TMP. Okay. Now, thymidine monophosphate by itself is what? Understood that the sugar here is deoxyribose. And the difference between uracil and thymine is the presence of a methyl group at number 5. Okay, the methyl group at number 5. So the source of the methyl group here is your activated methionine, which is known as your S-adenosyl methionine. So what is the purpose of the alteration? Actually, this is the same as your post-translational. So this is added after the nucleic acid has been formed, meaning to say after your RNA has been formed, then a change will follow. The purpose of which are threefold: direct measure of the turnover of nucleic acid in cells, for oligonucleotide recognition, and in regulating the half-life of the RNAs. Okay, half-life of RNAs. These are other examples. So as you will notice, methylating the base is common. Okay, is more common. Okay, this is your tRNA. The omega symbol there signify the pseudouridine presence in the loop. Then we have these free heterocyclic bases. We have hypoxanthine and xanthine and uric acid. Uric acid is the end product of purine nucleotide degradation. Hypoxanthine and xanthine can be an intermediate in that pathway. Then we have xanthine oxidase. Xanthine derivatives, xanthine derivatives wherein methyl group can be added at 1, 3, and 7. And these are present in nature, found in plant. One of that is theobromine, found in cocoa plant in your chocolate. Another is in coffee. Another is in theophylline, is found in tea. So it is up to you to determine which is which. Okay. Because it can either have 1,3,7 trimethyl xanthine, or it can be 1,3, or it can be 3,7 methyl dimethyl xanthine. Okay, that's it. Another thing is tautomerism. What does it mean? It refers to the attached oxo group and amino group. The predominant tautomer is the double bond O, and this is known as the keto form. The other form is enol form, which is OH. So for the O, it is double bond O or keto. For the amino, it is single bond H, CH2. Okay. Well, this one is H2 is a double bond H. Okay, NH2, not CH2, NH2. So keto form and amino form. These two are very important. The tautomerism together with the anti-beta and glycosidic configuration of the bond between the purine base and the pentose sugar is very important for the proper positioning of the complementary bases in DNA. Meaning to say, A hydrogen bond with G, and C will hydrogen bond with T. Okay. Oh no, GC and AT. GCAT, hydrogen bonding. So the concentration of the total nucleotide will be fixed with a narrow limit, and it is depending on the how much of each individual will varies depending on the cell type and the energy state. If it is at high energy state, then there is a lot of ATP. If it is at low energy state, then you can have ADP or AMP. Another property is it can absorb UV light close to 260 for the main reason of the presence of the conjugated double bonds in the ring. Okay. Treatment to alkali or acid. The N-glycosidic bond is said to be stable to alkali treatment. The purine bond, the N-glycosidic bond found in purine is very stable to acid treatment as well, but not the purine. So the purine is labile to acid treatment. Solubility-wise, nucleotide is more soluble than nucleoside, and nucleoside is more soluble than the free base. Can anyone tell me, this time I want somebody to tell me the reason for the nucleotide greater than nucleoside greater than free base in terms of solubility? What do you need to understand first? You need to understand what are the structural formula, meaning to say you need to understand what are the components present in each, and in each component what are the particular atom or substituent that will allow you to say why solubility is greater as a nucleotide than the nucleoside, and nucleoside is greater than the free base. Okay, so think of what do you see in your nucleotide? What is the difference between nucleotide and nucleoside? You have?
A phosphate group, Doc.
Very good. It's the phosphate group that give additional property for being more soluble. How about between the nucleoside and the base?
The sugar.
The sugar, what do you see in the sugar?
Hydroxide.
Correct, hydroxyl group. Okay, hydroxyl group, the OH attached to the carbon prime. Okay, very good. So those are the reasons, okay? And then take a look at the one below. So it is written with direction, meaning to say we start with the 5' and then toward the 3'. And that is the reason why the phosphodiester bond is referred to as 3' to 5'. Okay? Just like when we say that the protein start with N and then end with a C terminus. So the reaction, the alpha carboxyl group and the next alpha amino group of the amino acid in the chain. Okay, so there is the nomenclature is very important this time because there is no such thing as a 5' to 3' phosphodiester bond. It is always a 3' to 5' phosphodiester bond. Okay. Okay. So this is a condensation reaction. In any condensation reaction of forming a covalent bond, there is the elimination of one molecule of water. Now, all of this is actually in the book, and I think it is written in the first part, and then a few will be in the text, meaning to say in the biochemical importance part. So number 1, nucleotides are found primarily as the monomeric units of nucleic acid of the cell. There are 2 types of nucleic acid, your DNA and RNA. The difference is in the pentose sugar. In DNA, it is the oxyribonucleic acid, and the R is ribonucleic acid. So the precursor, the monomeric is in the monophosphate form. The precursor is in the ATP, triphosphate form. So the precursor for DNA, take a note, DATP, DGTP, DCTP, and TTP. As I mentioned earlier, TTP is already means the oxythymidine, what is the thymine? Nucleoside of thymine? TM, okay. So TTP, you don't necessarily have to put the D anymore. While RNA, as you will notice, the difference is that's why we say the uracil base is found only in RNA. But the thymine base is predominantly found in DNA because as we pointed out a while ago, you have also a TMP in your tRNA. And this is derived from addition of a methyl group by the S-adenosyl methionine to form your TMP on the tRNA chain. Okay. It serves as an energy stored for future use in phosphate transfer reactions, okay? Predominantly, this is carried out by ATP. So most of the condensation reaction in linkaging the monomeric unit in the macromolecule will require the use of ATP as the energy source. But in translation or protein synthesis, you have mostly what is used is GTP, and there is only one ATP that is used during the initiation step of replication. During the in translation protein synthesis. One ATP is used during translation, sorry. And you are familiar already, I hope you are familiar already with the different coenzyme form, that it is a component of your different redox coenzymes as well as your CoA. So what is present in NAD, NADP, and FAD is the AMP moiety, and what is present in CoA is the 3', 5' ADP. Okay. Control numerous enzymatic reaction by being an allosteric molecule in this reaction. What is an allosteric molecule? You have been told that allosteric molecule can attach to the allosteric site of an enzyme to either increase the substrate binding ability of the enzyme as well as increase the catalytic activity. It actually can go both ways, increase or decrease the function of the enzyme. And then it can also serve as a physiologic activator or mediator of numerous important cellular processes. We have the cyclic AMP and cyclic GMP, which is referred to as the second messenger in signal transduction. The first messenger are the specific hormone involved. It binds to the receptor and brings about signal transduction for a particular protein to function the way it should be. Example of cyclic GMP as a second messenger is in response to the formation of your nitric oxide, small molecule with many functions, okay? Then you have the GTP, GDP cascade events that is present in signal transduction. So meaning to say, the receptor is actually a G protein. It contains your GTP, GDP cascade. Then ADP by itself is a normal platelet aggregant, so can bring about the initial blocking of any tear in your blood vessel. Okay, so this is the illustration. I just want you to appreciate the illustration. So you have the epinephrine. It can attach itself in the beta or the alpha receptor of adrenergic receptor. So let's say it attached. By attaching, if you look at the one, below, the receptor is quite a big. It is an intrinsic membrane protein. The presence of the ligand, this time, this is a hormone or a neurotransmitter, it will bring about the activation of your adenyl cyclase. And then adenyl cyclase will act on ATP to form cyclic AMP. Then cyclic AMP will act on inactive cyclic AMP dependent protein kinase to make it active. And down below inside the cell where the ligand has bind to its receptor, it can bring about metabolic pathway from starting, okay, or a good example of this will be your glycogenolysis, the breakdown of your glycogen deposit in the cells, okay? And you have to appreciate the one below. You have the alpha, beta, and gamma, and then you have the GTP and GDP. So this is part of the G protein. And there is a change also in that particular protein, alpha, beta, and gamma, that can now bring about either effector, whatever need to happen inside the cell. Okay, so be familiar with this because there is a lot of this illustration in Harvard. Another is it serves as activated intermediate in numerous biosynthetic reactions. Okay, we mentioned about activated methionine, S-adenosyl methionine, so it is SAM, SAM, in metal transfer reaction. Another one, there is part of the S-adenosyl methionine which become the source of your propylamine that is important for the synthesis of polyamine, which is important for the DNA. Then you have your sugar nucleotides, meaning to say you have UDP, quite specific, UDP glucose, UDP galactose, GDP mannose, and GDP fucose. Then CMP sialic acid. If you want to form glycoprotein, you need all of these activated sugar nucleotides. There is no need for the role of ATP this time because the nucleotide itself is already active. If you just want to form glycogen, then you will just use your UDP glucose. If you want to form your lactose, then you actually have your GDP galactose. Okay? Mannose, glucose, and sialic acid are components of your glycoprotein as well as galactose and glucose. And you have seen this in the previous slide of Dr. Pipito, that to form your phospholipid, it has to be activated in the form of CDP, choline ethanolamine, and then to form your triacylglyceride, you need your diacylglycerol activated by CDP. Okay, then we have PAPS, 3' phosphoadenosine, 5' phosphosulfate. So this time it is for S transfer reaction for the formation of your glycoaminoglycan, which is part of unit 2, glycoprotein, also part of unit 2, sulfatides you have encountered in lipid chemistry, and conjugation reaction, which you also have you will encounter in xenobiotics and bilirubin metabolism. UDP glucuronide is involved in the conjugation reaction for bilirubin metabolism as well as xenobiotic or particularly drug metabolism. Okay. So, any question before we move on to metabolism? I will try to speak slowly in metabolism because the metabolic pathway, the de novo, is quite long. I do not expect you to know the name of each intermediate. What do I expect from the student to remember when they study the metabolic pathway of the de novo is to appreciate, first of all, how the nucleotide is being built. Okay, there are 3 components: the phosphate group, the pentose sugar, and then you have the base, a 9-ring, 2 by circular, 2-ring form attached to one another, and a single 6-membered ring. Okay, because the best way to study this is for you to be able to make a table of comparison of what is similar, that's one, and then a comparison of what is the different. Because if you know they are similar, you will actually need to remember one thing. What is the similarity? It happens, it is found in both. And then for the not similar, then you have to be more particular as to which is this particular precursor, why is it important. In addition to that, we also have to know what is the precursor of the substituent group. Okay, what is responsible for the oxo and what is responsible for the amino group. Okay, so those are the things that I expect you to remember so that you will be able to answer the question asked in the exam. Before I forget, let's go back to protein on your scrappy. I said it is from goat. No, it's not the goat, but it's from the sheep. Okay, the scrappy is your spongiform encephalopathy that happened in sheep. Okay. So dietary source, there are few actually or none at all that is incorporated into the tissue nucleotide. The reason for that is because the body can form it from precursor. Okay. So it can form it from precursor that is available in the body, or it can salvage the pathway. So when you say salvage, other component is already present and you just need the missing component. Now the rate of synthesis is subject to precise regulation. Okay, so the nucleotides produced in the appropriate amount at the time appropriate to meet the cell needs. So the metabolic pathway inside the cell is very precise and is well regulated, and it is not wasteful by going into what we call the futile pathway. You form and degrade right away. If it is forming, it is forming. If it is degrading, it is degrading, not at the same time. Okay, this is the differentiation between the de novo from simple precursor, and of course, the structure is quite complex, so it will need high energy input or more ATP is used. For the salvage pathway, we already have the nucleoside. So what is lacking is the phosphate, okay? So the enzyme is always a kinase if you are going to add a phosphate group. And the substrate for that phosphate is from ATP. Okay? Although there is a few always happening in the body, but there are always that happen in the body. So phosphorylation on the nucleoside is catalyzed by kinase in the presence of ATP. And then let's say you have a free base. So you need your ribose phosphate. Because the source is PRPP, phosphoribosylpyrophosphate, pyrophosphate, then the reaction is referred to as phosphoribosylation of the free base. Okay? The de novo pathway has to happen because there are certain cells in the body that would require a de novo pathway to happen. Okay, meaning to say the salvage pathway is not there, depending on the cell. Okay, so this is just one part of the purine nucleotide de novo synthetic pathway. Okay. After this, so this is linear, one after the next. I think it's better if you can open your book to this page so that it is easier for you to follow. But what I have written below is the structure of the purine ring with the numbering. Okay. First, the overall determinant of the rate of the de novo purine nucleotide biosynthesis is the concentration of PRPP. The more PRPP is present, then the more purine nucleotide synthesis will happen. Okay, so directly related to each other. So concentration of PRPP is important. Now the question we ask ourselves is, where do we get the PRPP? And that would be the first reaction. Okay, ribose 5-phosphate, the presence of ATP and magnesium. Magnesium is always there when you have ATP participating in the reaction, is the PRPP, phosphoribosylpyrophosphate pyrophosphate. So the first reaction is important, okay, because it is the reaction that involve your PRPP synthetase. This is not synthase, but synthetase. Okay, the difference between synthetase and synthase is if you use ATP, you call it a synthetase. If there is no ATP, then it is a synthase. So this is another error that I would like you to correct. And then after the PRPP is formed, glutamine is added. Okay, I hope you are following in the book and you are looking at the number, which become your N9. Let me see. I cannot see very well. Okay. So you're N9, okay? Why N9? Because you have learned in the structure that is where the pentose sugar is attached. So glutamine is an amino acid with a CONH2 in its R group. So the other product form obviously becomes glutamine and then the pyrophosphate group. So that it becomes now ribose 5-phosphate. Okay, attached to N9. So meaning to say, the ribose phosphate group is formed first, and then from the ribose phosphate moiety, you build the ring. Okay? But then purine has 2 rings, and N9 is part of the small ring. So obviously, the smaller ring is the one that is formed first before the bigger ring. Okay, another important point is the role of your tetrahydrofolic acid or hydrofolate. This is a derivative of your vitamin B9 folic acid. And this is the coenzyme form of B9, tetrahydrofolic acid. And what is the function of tetrahydrofolic acid? Is to carry 1 carbon group. So that is the function, to carry 1 carbon group. So the 1 carbon group that is carried this time is N5N10 methynyl tetrahydrofolate. Okay, and it will become what? Did we miss out on something?
Glycine daw.
Okay, very good. At least you are looking and listening. Okay. Okay, so after the N9, as I said, we will build a smaller ring. So glycine is added, and what have you noticed about glycine? It becomes your C4, 5, and and 7. Correct?
Yes,
So what
Doc.
is lacking is the C8. So the C8 is derived from the N5, N10 methanol group of tetrahydrofolate. Is that clear? And what have you noticed about the tetrahydrofolate? It is one of the product that is released. So its role is really just to carry the one carbon group. And then, is the ring closed or not? It is not yet
Not yet.
closed. Okay. You need to put in what? N3. Okay. And this time it also comes from glutamine. Okay. Glutamine. You try to see that you have all of that ATP there needed. Okay. So it becomes, so you now add the N3, then after which there will be closure. So the ring closure again will need energy. Then we continue to build now on the bigger ring. Then carbon dioxide will come in. So the reaction is obviously carboxylation. The enzyme is carboxylase. It will now become your what carbon atom? C6, right? C6. And then what follow after that is you will now add in your N1, correct?
Yes, Doc.
And the N1 will come from aspartate. I want you to remember it is aspartate that is N1, and it is the alpha amino group that is attached, okay? So it become a big molecule after that. So something has to be removed because the rest of the aspartate structure is not needed to form the ring. So it will be removed and it ends as a fumarate. Now fumarate is an important intermediate that is involved in the tricarboxylic acid cycle, or the TCA. And TCA is an important pathway for man because that is the common pathway wherein all nutrients, be it fat, be it carbohydrate, be it protein or amino acid, wherein it gets into that. Try to remember pyruvate is the end product of aerobic glycolysis. Then it has to be transformed into acetyl-CoA so that it can participate in the TCA cycle. And in beta oxidation, another source of energy for man is fat, which is higher, ends up actually as acetyl-CoA because you have a lot of CH. Okay. Then it will go to the TCA cycle, which is connected to your respiratory chain or electrotransport chain for the cell to form ATP. Okay, the pathway of producing ATP in the respiratory chain is known as oxidative phosphorylation. If it is in other pathway, it is substrate phosphorylation. Okay? Because it is oxidative phosphorylation is mentioned in the book. I want you to appreciate the meaning of oxidative phosphorylation and where is it mentioned and what is it for. Okay. So this is another thing that you need to remember. Aspartate becomes N1 and it gets out as fumarate. And then the reaction is adenylosuccinase, okay, to come out as fumarate. You remember this also. So the last atom that is missing is your carbon 2, okay? So for carbon 2, again, you need another molecule of tetrahydrofolate, this time carrying your N10 formyl tetrahydrofolate. And as you will notice, it will be the tetrahydrofolate will come out. Okay. Then after which you have your closure. And the end product that is formed is IMP, inosine monophosphate. So the first product, the first complete urine nucleotide that is formed is IMP. It is already complete. So what do you think will happen to this one? It will undergo a branch pathway wherein on one branch it will become AMP, on the other branch it will become the GMP. Okay? Is that clear? The thing that I want you to remember and appreciate as you study by yourself, you have to talk aloud, talking to yourself, telling yourself the story of the purine nucleotide, de novo purine nucleotide biosynthetic pathway. And I want you to remember, it's easy to remember about IMP cyclohydrolase because the end product is an IMP and it is cyclic and water is released, so cyclohydrolase. That is how to remember the reactions in the pathway and the name as well. Okay, so we move on and continue the pathway. So from IMP, it will become AMP. Take note. What are you taking note about? What do you have in adenosine? You have the 6 amino group, which comes from aspartate, that's 1. And just like what happened in the de novo pathway, it will contribute all, but eventually it will be removed as fumarate and becomes AMP. So you have the adenylosuccinate AMPS to become AMP when you remove the fumarate part. You have GTP that is needed for this reaction of IMP to adenylosuccinate. Then on the other branch, to form your the O at 6 carbon, you have your, what do you have? What happened here? You have a dehydrogenase. Okay, so there is the dehydrogenase. It, from IMP, inosine monophosphate, it becomes xanthine 5-phosphate. And then you add the amino group at carbon 2. This time it comes from glutamine. So you need a lot of glutamine to form your purine nucleotide de novo pathway. You also need aspartate as part of the ring and as part of the substituent group. And then from AMP to ADP to ATP, you need your kinases and you need your ATP. And take note of the participation of the ATP in the second reaction leading to GMP. Okay, why must you take note of this? Because that would be point of regulation. So in essence, this is the one that you are forming. Okay, the origin of the atoms in the purine ring system. Now, there is such a thing as a multifunctional catalyst. The reason for this is to facilitate, okay? Because there is a lot of reaction happening to form the compound, so it is to facilitate rapid and complete transfer of the intermediate. So these are actually adjacent catalytic sites, and this is brought about by gene fusion to ensure the production of equal amount of your different catalytic activity that are present one to another to facilitate the transfer of the intermediate. And there is 3 points in purine nucleotide de novo pathway. However, there is no specific name for that. But I think you can surmise as to what is happening here. After glutamine, you add your glycine, then you add the last carbon of the smaller ring, and then you close it. Okay? And then exactly it happened. You add carbon dioxide, okay? And aspartate to continue with the bigger ring. And then finally, you add the last carbon, and then you close the ring to form your bigger ring. And this is the regulation. This is the one that I want you to remember rather than the one that is in the book, which is quite confusing. Okay? The red one is feedback inhibition, meaning to say the product form can inhibit the enzyme further up. And this one, it has a feed-forward activation. And this is a very good example because most of the regulation in the pathway is feedback inhibition, meaning to say, once the product is enough already, the product itself will stop the reaction at different point, okay? Because there is no need to form more because it has already enough. So feedback inhibition. Can anyone who can name the enzymes after PRPP synthetase? When we add the glutamine.
Glutamine phosphoribosylate amino transferase, no?
Amido transferase. So these are your PP, glutamine, PRPP, glutamine amido transferase. So this is the rate limiting enzymes or the committed step. Meaning to say, once the product is formed, it has no other way to go but to become AMP or GMP. It is committed to go to proceed the pathway into the product that it requires. Okay, so you have the first and the second enzyme, right? And then the last one, your AMP cyclohydroxylase, that is the last one. So you will notice that most of these are, so PRPP, the substrate itself, will favor the presence of the substrate, okay? Is a positive activator or allos activator of the rate limiting enzymes. Then the end product is AMP and GMP, right? And then it will inhibit the first reaction from IMP. It will also inhibit the ADP. You follow the arrow. So the amidotransferases can be inhibited by GMP, GDP, and GTP, likewise on the other side. But the PRPP synthetase is only inhibited by ADP and GDP. Are you looking at it? It is easier to remember rather than the one in the book. It's quite confusing. Okay. Okay. So we move on to pyrimidine. Now in pyrimidine, the multifunctional enzyme has a name. Your CAD enzymes and your UMP synthase. So it has a name. So the first reaction is glutamine plus carbon dioxide and 2 ATP. The enzyme here is carbamoyl phosphate synthetase 2. If there is a 2, there should be a 1, correct? You cannot just name the enzyme as the number 2 enzyme if there is no number 1. So the carbamoyl phosphate synthetase 2 is cytosolic. The carbamoyl phosphate synthetase 1 is mitochondrial enzyme. Okay, that is the difference. And instead of glutamine, it has ammonia. So what is this cycle? Which is partly mitochondrial and partly cytosolic, the reaction. So carbamoyl phosphate synthetase 1 is in the mitochondria and it is the first enzyme to form the urea cycle or the first reaction, catalyze the first reaction, okay? So the product here is obviously your carbamoyl phosphate. Then what will happen to carbamoyl phosphate? You will add aspartate, everything, which is known as your aspartate transcarbamylase. Okay, then after that, you close the ring by a dihydroorotate, and the product is dihydroorotate. So the C is carbamoyl phosphate, aspartate transcarbamylase, and dihydroorotate. So it stands for these 3 enzymes, CAD. So the first 3 reaction of your pyrimidine nucleotide de novo pathway. Then after that, the dihydrofolate will be oxidized to become orotic acid. Okay? So we have the ring form already in pyrimidine, correct? But what is lacking now is your ribose phosphate. So you need to add that. So as an intermediate orotic acid, you can now add the ribose phosphate group, and the source is PRPP. Okay, are you following? PRPP, and then the end product of the OPRTase is your OMP, orotate monophosphate. So the first complete pyrimidine nucleotide by way of the de novo pathway is still not a mature pyrimidine nucleotide. You follow? Because you don't have OMP as part of your any of your nucleic acid. So what will happen is there will be a decarboxylation and it will become UMP. Okay, so you now have the 1 major pyrimidine base, your uridine monophosphate. So the multi-enzyme here or catalyst is known as UMP synthase. It is made up of OPRTase and OMP decarboxylase. Okay? But how many pyrimidine do we have? We have 3. We still have to see how cytosine is derived at and how thymidine is derived at. Okay? Okay. So, to form see the cytosine part, okay? You need glutamine and you need ATP. Obviously, the enzyme is a synthetase. What is important in enzymatic reaction is the substrate specificity that the substrate should be into, because that is how the enzyme will be able to recognize the substrate. So after UMP, you add another phosphate group through a kinase and ATP, another phosphate group through a kinase and ATP. So you now have UTP. Then as UTP, the CTP synthetase can now act on UTP to now form your CTP. So the source of the amino group here in the cytosine is from glutamine, right? It is from glutamine. How about TMP? First, the substrate has to be in the deoxy form. Okay? So meaning to say, UMP actually has to become something else before the deoxy can be, the ribose can be changed to a deoxy form. Then as another reaction, it becomes the DUMP. Then in the presence of timely delayed synthase and in the presence of N5N10 methylene tetrahydrofolate, it will become TMP. Okay, there is actually no need to write the D, TMP. And what have you noticed about the role of tetrahydrofolate this time? It is oxidized to a dihydrofolate. So the reaction referred to as the dihydrofolate reductase in the presence of NADPH plus H will reconvert your dihydrofolate to tetrahydrofolic acid. And can you now understand what will happen to the cell if DHFR or the reductase, the hydrofolate reductase is absent? Because for purine and pyrimidine to happen, tetrahydrofolate molecule has to be present. Is it not? If you will not convert it back, meaning to say, you cannot form DNA, you cannot form RNA as well. So it will kill the cell. Okay? You understand the consequence and the importance of the dihydrofolate reductase action. So if a drug inhibits dihydrofolate reductase, it in one way or another will decrease the division of the malignant cells. Okay, so there are how many things? It has to be in the deoxy, UMP is the substrate, then you have the enzyme, and then the role of the tetrahydrofolate, wherein there is a change, and there is an important enzyme that need to convert it back to tetrahydrofolate. Okay. So this is where the atoms come from. So the N3 is actually from glutamine and the C2 is from carbon dioxide, and these two are referred to as carbamoyl phosphate. So that is the one that is formed first, followed by the addition of both carbon and nitrogen atom. So what is the counterpart of aspartate in ring formation in purine, wherein the nitrogen and carbon atom of the amino acid becomes part of the ring? The answer is glycine, right? You have glycine in purine, while in pyrimidine, it is aspartate. That is what I want you to do this afternoon. to make a table to see the similarity, another table to look at the difference. Another difference obviously is the what will happen to the tetrahydrofolate molecule as it bring in, because methylene is CH2 and then what is in thymine is CH3. Okay, that's why it will contribute and it will become dihydrofolate. That is the reason why it becomes dihydrofolate. Okay. The substituent group, what are being added, all of that. Okay. And take a look at the control mechanism. The first reaction in the pyrimidine de novo pathway can be inhibited by the purine nucleotide. Okay. Negative. And also the important PRPP synthetase can also be inhibited by both purine nucleotide as well as TDP, so the diphosphate group. Okay. Now I have put here allosteric and coordinate repression and de-repression of enzymes. So we mentioned about allosteric mechanism in the regulation of the enzymes involved in purine. But this time in pyrimidine, it is both allosteric as well as coordinate repression and de-repression of enzyme. What does it mean? Repression and de-repression or expression. These are terms that refers to the expression of the information that is found in the DNA. So this is at the gene level, okay? At the gene level. So normally, the most likely, the enzymes involved in the de novo pathway of pyrimidine nucleotide is normally repressed. So meaning to say, there should be the purine happening followed by the pyrimidine because it can also de-repress. So there is now no inhibition to translate the information that is in the DNA to form now your pyrimidine nucleotide de novo pathway. Okay. ATP, which is a molecule of your purine, is positive on your carbamyl phosphate transcarbamylase on the second enzyme. See, it is positive because it allows it to happen. And then take a note again, a GTP, which is also a purine, is positive on the CTP synthetase, so allowing CTP to happen. So there is a coordinated regulation happening, right? Okay. Moving on, salvage is very easy. I want you to remember only, I think you will remember SGPRtase, which is hypoxanthine guanine phosphoribosyltransferase transferase, the one above. It will convert your hypoxanthine to inosine to IMP, then it can become AMP or GMP, or it can act on the base, which is your guanine, to become GMP. Okay, so that is the purpose of this enzyme, SGPRtase. So the source of your ribose phosphate again is PRPP. Then the other one is the presence of the nucleoside to become your nucleotide. So you need only to put the phosphate group. So the enzyme is a kinase. So we have uridine, cytidine kinase. And the source of the phosphate group is ATP. That's why it comes out as ADP. So uridine become UMP, cytidine become CMP, then you can plus more of the phosphate group. Okay. This one is very important. I have known about this cycle when I read other biochemistry book, but I usually don't like to include this, but this time it is now present in Harper. And it is very important because the cycle will generate an important intermediate in the TCA cycle, and that is your fumarate. And you have learned a while ago that aspartate can become fumarate. Okay? So the net effect of the deamination of aspartate is to produce fumarate that can become an intermediate in the TCA cycle. This is what we call anaplerotic reaction. Any reaction that will give rise to an intermediate of the TCA cycle is referred to as anaplerotic reaction. This is very important in the muscle cell because the muscle lacks most of the enzymes of the major anaplerotic reaction. And the muscle cell is what? Muscle is protein, right? Actin, myosin. So it can get the aspartate, okay? And then because of this purine nucleotide cycle, it can also lead to TCA cycle activation. Continuous because muscle to be active even at rest will actually need, you have the tone has to be maintained, okay? And then when it contracts, the more you need your ATP for muscle contraction. That is the reason why the connection of what happened, okay? So what is lacking in the anabolic pathway? We talk about the long process or the long pathway, and we talk about the short pathway. And the long pathway has to happen because some cells do not have the salvage pathway in them. Okay. Then the difference between the two, the importance of the multi-catalyst actions on the long pathway so that it will happen coordinately well. And then how each other, the purine and the pyrimidine, regulate each other pathway. And we talk about the short pathway, which is actually very easy to remember. And then we have on the side the purine nucleotide cycle happening in the muscle cells. Okay. So what is lacking is how do we form the deoxynucleotide? The deoxynucleotide that was mentioned is only the TMP that is formed. Okay. So important is the substrate. The substrate has to be in the ribonucleoside diphosphate. Okay, remember it has to be in the diphosphate, not monophosphate, not triphosphate. The ribonucleoside reductase will act only on the ribonucleoside. Okay? Okay, so you need only one reaction depending on the specific, what is the ribo there that is present, and the nucleoside that is present. And then the reductant, the immediate reductant is the reduced thioredoxin. So this is a redox, so it will be oxidized. So you need again to convert it back to the reduced form. And here we are, thioredoxin reductase. Do you remember this? What type of a protein is this? This is a protein wherein each amino acid has selenocysteine, the 21st amino acid. Okay? So it will be reduced back to, so we call the reduced thioredoxin as the immediate reductant, and we refer to NADPH plus H as the ultimate reductant. Okay? Because you need this molecule to form more reduced thioredoxin. Otherwise, it will compromise the activity, the function of the cell. Now, DATP is an inhibitor of all of the ribonucleotide reductases. This is what I want you to remember from this slide. The specific substrate, the specific enzyme, the immediate reductant, the ultimate reductant, then what is thioredoxin, a selenoprotein, and what is the inhibitor of the all, it is DATP. Rather than memorizing this one. Okay, this is from the book. I don't want you to memorize that. Suffice it to know that the DATP inhibit all. And take note, you don't have the T here. The T comes from the uridine. Okay? Because you don't actually have a uracil in DNA. What you have is your thymine. You get the connection? Okay. This is just to show you that these are your precursor of DNA. Okay. Now synthetic, oh my God, what time is it? It's 11. I will just continue very fast. Okay, the synthetic nucleotide analog is used, it has therapeutic potential. And what is the mechanism of action of these analogs? First, it will inhibit specific enzymes activity involved in the formation of nucleic nucleotide and DNA. So that's one. Inhibit the specific enzymes involved in the synthesis of nucleotide and DNA. Second, it can disrupt the normal replication by interfering with the formation of the Watson-Crick base pairing, G to C and A to T. Okay, so this is the normal pairing. It will disrupt the normal pairing. So if it is going to affect the synthesis of DNA, it will actually kill the rapidly dividing cells, which we see in tumor cells and viruses. So it can act as an anti-malignant agent or antiviral agent. Okay. Actually, since we use a lot of glutamine, a glutamine antagonist obviously can interfere with your nucleotide anabolism. Okay. Inhibit the amidation reaction. Azathioprine and diazonoleucine, these are the example. Then antifolate, this is the one that will inhibit your dihydrofolate reductase. And a good example is your methotrexate, which is used as an anti-malignant agent. Trimethoprim is used, this is part of your antibacterial. Then anti-metabolite is affecting structural analog. Okay, that will inhibit specific metabolic site. Example of which is your, okay, we have here now the fluoro 5-fluorouracil. Okay, that will inhibit your thymidylate synthase. So 6-mercaptopurine has to be converted to a nucleotide form, and it will become a negative effector for your rate-limiting enzymes, as well as your IMP dehydrogenase to form GMP, and on the other side, your adenylosuccinase to form your AMP. So rate-limiting form and at the branch point. Okay, antiviral agent. A good example would be your ACT as triphosphate inhibit reverse transcriptase. Some of the viral agents are RNA, and it has to undergo reverse transcriptase action to become DNA. So if you inhibit the actions of the enzyme, it can act on the activity of the virus. DDI and DDC is important for your AIDS virus. Okay. Then the change might not be on the change can be on the pentose sugar. Instead of your ribose, it is arabinose, so it become arabinoside. Inhibit DNA polymerase, so replication cannot happen. Then as ARA-CTP, again, it will inhibit your DNA polymerase. Now, 5-fluorouracil as a triphosphate form, it will inhibit the maturation of 4,5-S RNA. So in essence, the ribosome cannot be well formed, and then obviously it will affect translation of a lot of enzymes. Okay. Okay. I want you to show this one. The structure shown here is your allopurinol. An allopurinol will inhibit your xanthine oxidase to prevent the formation of a lot of uric acid. So this is a treatment for gout and also for transplantation to reduce the likelihood of rejection. We give azathioprine, which can be converted to 6-mercaptopurine, which can inhibit your 3 level of your purine de novo pathway. Okay, we now go to catabolism. We will not bother ourselves with this one because the product form are all soluble. But we should be concerned about purine nucleotide catabolism because there are 2 immunodeficiency that can happen if adenosine deaminase is deficient or low. Then it will lead to combined immunodeficiency, both the B cell and T cells. However, if it is the purine nucleotide phosphorylase deficiency, it will lead only to T cell immunodeficiency. Do not ask me how come. It is very particular to affect either the T cell or the B cells, okay? Suffice it to know that the catabolic enzymes involved in the breakdown or degradation of your purine nucleotide, if these 2 enzymes are deficient, then immunodeficiency will happen in the person. So try to find out which part it will happen. Then we mentioned about xanthine oxidase, okay? So you have your hypoxanthine acted by xanthine oxidase, and then guanine acted by another enzymes of the xanthine oxidase again to form finally your uric acid. And why must we worry about the uric acid? Okay, because of this. So the serum level of uric acid, I am not very particular about numbers, but you have to know that the serum level below 7 milligram per 100 ml, that is the normal level that should be found in the serum of a person. If ever it is more than this number, then there is now hyperuricemia in the person. And this can give rise to acute gouty arthritis. It can give rise to renal stone, your uric acid nephrolithiasis, and it can give rise to deposition as tophi in cartilages. Okay. Now, uric acid is normally excreted by way principally of the kidney. A few can also be excreted out by way of the gut. Okay. So hyperuricemia may be caused by either overproduction. So a lot has of the reason now why there is a lot of uric acid that is degraded from nucleotide is because there is a lot that is also formed of the purine nucleotide. Ergo, a lot of the catabolic end product of uric acid is also formed. That's one. So it will accumulate in the body. Second one, knowing that it is excreted out in the body system normally by way of the kidney, majority of it is by way of the kidney, then you have a reduce in the rate of renal excretion. Okay, very logical. Then it is divided into two, a metabolic hyperuricemia or a renal hyperuricemia. Metabolic, so something is wrong with the metabolic pathway. Renal, something is wrong with the kidney ability to excrete it out. Okay. There is primary and secondary metabolic hyperuricemia. Primary means there is increase in the production, ergo there is increase in the degradation. And take note that the rate of the de novo synthesis, as we mentioned, is the availability of PRPP. Now, when do we call it a secondary hyperuricemia? The increased turnover of the nucleic acid that can be seen in certain clinical conditions such as leukemia, polycythemia vera, and sickle cell anemia and psoriasis will lead to a secondary hyperuricemia. Okay, these are the different primary metabolic. We have here PRPP synthetase. Most of the metabolic disorder usually will tell you that it happens because there is enzyme deficiency. And it is not true when we talk about the primary metabolic gout if the enzymes involved is PRPP synthetase. Because the rate of the purine de novo pathway will become very high if there is a lot of PRPP. So, what is the nature of the defect this time? First, it has increased Bmax. Then there is resistance to feedback inhibition. Then there is low Km. Low Km means there is increased affinity for ribose 5-phosphate to form PRPP. And then this time we go back to the deficiency stage. Partial deficiency of your SGPRase is gout. And complete deficiency of SGPRase is another peculiar metabolic disorder known as Leach-Nyhan syndrome. And even deficiency of glucose 6-phosphatase, which can throw glucose into the circulation by removing the 6-phosphate group, known as your Bonger's disease, can also lead to hyperuricemia. Okay. So this is the Leach-Nyhan, the complete loss of your functional SGPRase. Okay. This is unfortunately sex-linked, so you see this in boys and not in girls. They exhibit symptoms, of course, of gout, but there is also nervous involvement, neural malfunction of the nervous system manifested as self-mutilation and mental retardation, and often they do not reach the age of 20. So meaning to say, if you see a boy, when they are put on the crib, how do they, they will bite themselves, they will bang their head. So self-mutilation will happen. The opposite of hyper is hypo. Obviously, if the enzyme xanthine oxidase is deficient, then it can lead to hypouricemia, and what will happen to the accumulated xanthine? It will be excreted out, and this time it can also lead to renal stones. Okay, this is not in your book, but this alone will tell you everything. If there is no glucose 6-phosphatase in Bone-Gert's disease, which is a glycogen accumulation disease, actually, what will happen to the glucose 6-phosphate? It will be diverted to the HMP shunt, and it will result to the formation of ribose 5-phosphate. So this is one of the characteristic or one of the products of HMP shunt, important product to give rise to ribose 5-phosphate. And with the different variant, it will lead to increased PRPP. It will lead to increased breakdown, either by the de novo pathway or by the salvage pathway. So there is increased uric acid. I have put here on the other side your Leeds-Nyhan syndrome if it is complete absence of hypoxanthine, the HGPRTase. Okay. And then, okay, renal. So something is wrong with the function of the kidney. It's either there is increase in the reabsorption because it can be excreted out. So increase in the reabsorption of uric acid in the pathway of the tubules when it moves up in the tubules of the kidney, or it will increase in the formation of your lactic or organic acid because it will compete for the secretion of your uric acid. Okay. Number one mechanism is increased reabsorption, exemplified by your thiazide, which is an antihypertensive agent, a diuretics. Then number two, compete for secretion or excretion is exemplified by your ASA or aspirin, and pyracinoic acid is a byproduct of your anti-TB drugs. Okay, another anti-TB drugs. So organic acid, even not your lactate or ketone bodies, will also interfere with your urate secretion. So you may have accumulation of ketone bodies if your diabetes mellitus is not well controlled. And that is one of the complications. You will go into ketoacidosis. Then in alcohol intoxication, the reason for the alcohol intoxication is it will produce your reductant. There is reductant that is formed and it will convert pyruvate to lactate. So there is a lot of lactate that can compete with the uric acid for excretion. And that is one of the reasons why the clinician will tell the alcoholic, if you do not want to suffer from the pain of your gouty toes, then stop drinking alcohol because it will aggravate. Okay, likewise with starvation, it will actually produce a lot of lactic acid. And obviously in any chronic renal disease, eventually which will compromise the function or the physiology of the kidney, it will lead to renal hyperuricemia. Okay? Never mind about this. You just read on this. I did not include this in the exam on Tuesday, but we still have the unit exam, we still have the bi-monthly exam, and we still have the final exam. Okay. try to appreciate what is being said here actually. It is like this. Any enzyme that is deficient will lead to the accumulation of the intermediate where it is supposed to act on. And what will happen to this intermediate if it is increased? Will it have an effect on the body? And will it have an effect on, and how is this excreted? That's why it is usually shown in the urine as hyperbiliruria. Okay? So that is how you have to appreciate in your study, to give meaning to the word, to the keyword that you want to remember, rather than memorizing everything which you are capable of at your age, but eventually, unfortunately, if this happens, it will not bring the knowledge to the point of the further examination that I mentioned a while ago. And I am sad every time when we do the promotion, it is always the final examination that in one way or another that will pull down your grade, which we don't want to happen. So the key here is try to study well and control the way you are studying. Okay, so good luck to everyone. You have one whole day to study well, so make good use of your time. I'm very sorry for the overtime.
I will just announce when, or because Dr. Salces unfortunately has a procedure right now and he can't come in. Hindi ba sir? Wala. So, if you have like particular questions, Dr. Salces, can you email it to him? He can answer. And then if you really need a clarifying lecture, then we will schedule before your exam. Fortunately, at this time, because he has a scheduled procedure.
Doc, good morning.
Yes.
Aren't we supposed to have Dr. Salsa's corre next week, Doc?
Oh, it's not today?
According to schedule,
No.
Doc, it's supposed to be next week.
Is it not included? You try to see if is it not included in the grade?
And DNA and RNA are not included, Doc. Up to
Okay.
nucleotides lang.
Okay. So if it is not included, then you try to see the Gwen. Okay, I have made my question na ba, gamay. So I don't
It's not on the exam grade, Doc. It's up onto nucleotides lang, Doc, for the long exam 2.
Okay. So part pa ang nucleic acid for unit exam.
Yes, Doc.
Okay. So you can rest na and
You
have your
the
lunch.
exam read with you? I think part of the unit exam read, I'll confirm that one.
Murag appeal ba yan na ha? I will try to check.
Yes. Sorry, my internet is really bad on my side. But
I will try to see ha.